Hello. Hello. Excellent. Okay, so let's start. I have a few people in. Okay. Can you tell me, please, are you familiar with the sigma notation? Yes or no? Sigma notation. Have you heard about it? Do you understand what it is? So today we're talking about sequences in series, so it's maths today. Kind of. Is there anyone who haven't heard of sigma notation? Whatever you, just let me know, please. Can everyone reply so that I know where to start? Sigma. Not really heard of it. That's a contradicting statement, but okay. I've heard of it. Okay. Notation. Sigma notation is a way of writing down sums of sequences. Okay, so this notation works like this. Sigma, this is a Greek letter sigma. Let's say I is 1 to, let's say, 4. And here we have something that contains I, typically. So for example, it could be I squared, right? So what this means that I takes values from 1 to 4, and this symbol means sum. It's the sum of I squared from 1 to 4. So literally means we take all the values of I from 1 to 4, square them and add them. So it's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared, and that's it. You can calculate that as 1 plus 4, 5, 13 plus 16, 29, is it? 29? I might be mistaken, but okay. Does that make sense? Do you understand what I've just done? Okay, Mark Rubik Shita. Might be 30. Yeah. So 4 plus 9, 10, 14 plus 16. It is 30. Sorry. See, I'm a bit off. Yeah, okay. So it could be anything. So for example, sigma AI from I is 3 to 7. That literally means A3 plus A4 plus A5 plus A6 plus A7. We don't know what that is. Probably some numbers, but doesn't matter what it is. You could have sigma of 2, I from 2 to 4, and that's very simple because 2 doesn't contain I, so it's going to be 2. That's 2, 3, 4. So if you see something like this, it's literally that. Does that make sense? So this is for I is 2, this is for I is 3, and this is for I is 4. But since the number doesn't contain I, it's always 2. It's like a for loop in Python. It's a very specific loop in Python, yes. It's a for I equals I in range 2 to 5 in this particular case, because there's a for. Well, you need sum is equal to, yeah, 0. Sum is equal to sum plus I, something like that. But yes, sort of like in Python. Okay, let's delete that, just not to confuse people who come in later. But yeah, so it's sort of a loop in Python. And okay, a simple one. Show that the sum of this, the sum of 1 from 1 to n is n. Well, that's very straightforward, because if we take the sum of r equals 1 to n of 1, so we start from 1 and finish at n, so it's 1 plus 1 plus 1 plus 1 plus etc. plus 1. So this is n equals 1, 2, 3, 4, and we finish with n. So this is n times, and n times 1 is, unsurprisingly, n. All right. Does everyone understand? Does everyone understand what I'm doing? Excellent. The sum of r from 1 to n is this expression. Okay, let's work out what this means. So sum of r from r equals 1 to n. So that starts from 1 and then finishes at n. So it's 1 plus 2 plus 3 plus 4 plus etc. plus n, and that has to equal to something. Okay. Well, we don't know what it is. So let's assume that it is S, a sum, S. What we're going to do, so we want to know what this equals to, right? Some of you already know that this is that, okay? Who knows that these are actually triangular numbers? It's a sequence of triangular numbers, but do you know this formula? Are you familiar with it? Yes or no? No, haven't seen it before. Okay, oh, that's good. That's exciting. So we are looking to find a formula for the sum from of numbers from 1 to n. So literally, 1 plus 2 plus 3 plus 4 plus 4 plus 4 plus etc. plus n. What I'm going to do is I'm going to rewrite the whole thing in reverse order. So I'm going to write down n plus, what's the previous number before n? Which number goes before n? N minus 1, yeah. N minus 1 plus n minus 2 plus etc. plus 3 plus 2 plus 1. And that's also equal to s, because, well, duh. Now I'm going to add them. I'm going to add the two. So the first one is going to be n plus 1. N plus 1. So I'm going to add the first number and last. Well, first and first. Then I'm going to add these two numbers. plus 2 plus n minus 1 plus, then I'm going to add these two numbers, 3 plus n minus 1 minus n minus 2, sorry, plus, etc. And at the end, it's going to be n minus 2 plus 3 plus n minus 1 plus 2 plus n plus 1. And that's equal to 2s because I've added 2s, s plus s. Okay. Is everyone on the same page? Have I lost anyone? Now, when I simplify that, there's going to be n plus 1 plus, this is also n plus 1. This is also n plus 1 plus n plus 1 plus n plus 1 plus n plus 1. And that's equal to 2s. And when you analyze, you will see that this is n times n plus 1. Literally n times. So it's going to be n multiplied by n plus 1 is equal to 2s. And from here, s is equal to 1/2 multiplied by n plus 1. So we've found a formula. So we proved, thus, the sum of r from r1 to n is 1/2 n plus 1. Okay. Well, that's what who was it? Was it Gauss? Famously. Gauss, yeah. There's no set rules. You kind of have to be creative. Try to see a pattern. But you can use standard results. For example, we know the standard result for r. There is a standard result for r squared. R equals 1 to n. And I think that's, I don't remember this one, but there's a formula basically. You know some formulas, and then at some point you just start guessing. Not guess, well, doing educated guesses what the formula is going to be. But yeah, that implies, so this means, for example, the sum of r from 1 to 100, the sum of numbers from 1 to 100 is, well, that is 1 plus 2 plus 3 plus etc. plus 100, has to be 1/2 times 100 times 101. This is 50 times 101, which is 5050. So the sum of the first 100 numbers is 5050. And Gauss, well, there's a legend that Gauss figured it out when he was in primary school. So how did he do that? Well, exactly the same way as we did. Well, sorry, in a very similar way as we did. So he wrote 1 plus 2 plus 3 plus etc. plus 100. And he said, okay, let's combine them. Let's do the first and last. So 1 plus 100 plus 2 plus 99 plus 3 plus 98 plus etc. And the last one is going to be 50 plus 51. And he worked out, oh, this is going to be 101 plus 101 plus 101 plus etc. plus 101. And that's 50 times. 50 times. And so that's equal to 50 times 101, which is 5050 Gausses. Gauss's string. So yeah, the legend goes that the teacher was very was wanted Gauss. Gauss is a famous mathematician. Wanted Gauss to get off his back and give him a task of adding all the numbers from 1 to 100, hoping that this will take Gauss the whole lesson. But Gauss did it in just a few minutes, and that is the origin of this legend. I wouldn't know how true it is. But we have these two formulas now, which we can use. Right? This is really good, and we can use them to find this sum, for example. Oh, of course, we could do the sum. Let's do it in two ways. So for A, the sum from 1 r equals 1 to 4 of 2r minus 1. So we just substitute 1. So it's going to be 2 minus 1. That's going to be 1 plus. Okay, let's do it properly. 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus 2 times 4 minus 1. And that is 2 minus 1 is 1 plus 4 minus plus 3 plus this is 5 plus 7, which is 4 plus 9, 16. Okay? But alternatively, we can do the following. The sum of 2r minus 1 from 1 to 4 is 2 times the sum of r from 1 to 4 minus the sum of 1 from 1 to 4. So we break it down into two sums. We're allowed to do that. Why we're allowed to do that, I'd leave it to you to prove. So the sum of 1 to 4, we already have the formula. It's 2 multiplied by 1/2 multiplied by 4 multiplied by 5. So times n plus 1. We're using the formula here. And we're using the formula here minus 4. So 2 times 1/2 is 1. 4 times 5 is 9. 9. Oh, sorry. Well, 4 times 5 is 20. 20. 20 minus 4 is 16. No. Answering Zeno's question. If there's a coefficient, no, you can't always put it in front of the function. For example, if you have the sum of 2r from r equals 1 to n, this is equal to this is equal to 2 sum of r 1 to n. This is allowed because the sum is linear. It's a property of linearity. But let's say if you have the sine of 2x is not equal to 2 sine x, because sine is not linear. So some functions or operators, in this case, sum is not a function, it's an operator. Some operators are linear, some operators are not linear. Okay, does that make sense? Linear means you can take it out, and non-linear means you can't. Yeah, but 3x, look, 3x, y equals 3x is a linear function, right? It's a linear function. It literally, it's a straight line, linear function. Therefore, you could take y equals 3, well, x, you could take it out. But yeah, there's a few linear things that you will encounter. Integral is linear. So what operators are linear? Well, first of all, the integral. Integral. You don't need to know what an integral is. Integral of a plus b is integral of a plus integral of b. That's what linear means. So derivative of a plus b is derivative of a plus derivative of b. Okay, what else is linear? Limits. Limit a plus b is equal to limit of a plus limit of b, because these are all linear, right? Not linear. Linear. Sine a plus b is not sine a plus sine b. Square root a plus b is not square root of a plus square root of b. Logarithm of a plus b is not logarithm a plus logarithm b. Right? You don't need to know what these are. So, but the idea of linearity, I really hope I've managed to put across. Yeah, got it? Okay, nice. B. B, the sum of r equals 1 to 50 of r. That is 1/2. We're using the formula of 50 times 51. So it's 25. No, it's 1/2 multiplied by 50 times 51 is 2,500. 2,550. And times 1/2 is 1,275. Wow. Okay. I'm impressed by me. Now C. How would you do this one? R equals 21 to 50. You've already done this one. Yeah. Oh, Luke, excellent. Yes, of course. You do the sum from 1 to 50 of R, and then you subtract the sum from R1 to 20, not to 21, but to 20, because you start with the 20 first. All right? Of R. And that's 1,275. You already did this one. And then minus 1/2 times 20 times 21. And that is 1,275 minus 210, which is 1,165. No, 1,065, sorry. 1,065. Okay, right. Is that the year of the Norman invasion? Almost. Okay. Now we have a formula, and you need to work out what's in here, basically. It's the sum of something. The question is, what is that something? Okay. How would we approach that? Ooh, it is the square of the formula that we have already used. Very good. That's very observant. Thank you. It is. That won't help us in any way, but that's a good point. N plus 1 squared. That won't really help us. But yeah, it is. Well, there is a question in the assignment. In the assignment, there's this question. Question 9, problem 9. Sequence is defined as, find an expression for n in terms of n. You basically need to work out this this expression. Well, it's actually not that hard. But you do need to yeah. So you need to do, what if n is 1? Suppose n is 1. Then it's the sum from I is 1 to 1 of AI, and that's literally means A1, right? So the first term, and then you sub in 1. So it's going to be a quarter times 1 times 2 squared. So a quarter times 1 times 4, that is 1. So the first term of the sequence is 1. So A1 is 1. That's good. Suppose n is 2, and then the sum from 1 to 2 of AI is A1 plus A2, and that's equal to 1/4 times 4 times 3 squared times 9. 1/4 times 4, so that's going to be 9. So what is A2? 8. Very good. So if n is 3, 1 to 3, AI is A1 plus A2 plus A3. And then using the formula, so that is 1/4 times 9 times 16. So that's 4 times 9, 36. So what is A3? $27. Do we need to do N4? These are the cubic numbers, yeah. These are the cubic numbers. So AI is I cubed, or for simplicity is N cubed. But that tells us an interesting thing. If you take the sum of R from R equals 1 to N, that's going to be 1/2 N plus 1. But if you take the sum of R cubed of cubic numbers to N, it's 1/2 multiplied by, 1/4 multiplied by N squared multiplied by N plus 1 squared. That's quite fascinating. Okay, that is good. I think that's it for series for today. Now I want to talk about sequences. So a series is a sum of a sequence. Okay. What does it mean when we say a series is converging? Well, it's quite an intuitive thing. So, for example, if series is converging, well, we can say, for example, a sequence is converging. So 1 divided by n is converging, because 1 divided by n is 1, 1/2, 1/3, 1/4, 1/5, etc. Then this is converges to 0. Right? Do you understand what I mean? That it converges to 0? It gets closer and closer to 0 with every step. Okay. Ruby? Okay, so if you take a number line, this is 0, this is 1, this is 1/2, this is 1/3, this is a quarter, this is a fifth, etc. So you get closer and closer and closer to 0. This can be written as the limit of 1 over n as n tends to infinity is 0. Or you can say 1 over n tends to 0 when n tends to infinity. Or you could simply say, or 1 over n converges to 0. It's the 3 different ways of saying the same thing. I personally prefer the first one. Okay. There's a strict definition of convergence. You don't have to understand it very well. I will spend some time going through that. But let's see if we can figure out whether these sequences converge. There are different ways of how we can do this. So one way of doing it is using Excel. So let's see, the first sequence is N. So this is N. And this is the sequence, so AN. So 1, 2, 3, etc. And then AN, I'm going to zoom in. 1 AN is going to, this is going to be equal to 10,000 multiplied by N divided by, open bracket, N squared plus 1. And the first term of the sequence is 5,000. Second term is 4,000. Oh, surprising. Is it? Okay. Carry it on. So you can see it's always decreasing. Looks like there's no, oh, it looks like there is a limit. So you can see after 2,550 steps, we could insert charts. Yeah, it looks like it starts with 5,000 and quickly drops and then goes to 0. So I'm pretty safe to assume that the limit of this sequence is 0. Limit of 10,000 n divided by n squared plus 1 as n tends to infinity is 0. I'm not doing any rigorous proofs. How to know that it's not a negative number? Well, we can analyze and see that this n squared plus 1 is always positive, and 10,000 n is always positive. Positive divided by positive is greater than 0. But yeah, that's a good point. We say it's bounded. This sequence is bounded and it's monotonic. It's monotonic and it's bounded. So monotonic means every term is smaller than the previous, but then there's a lower limit. It cannot go past 0. So there must be a limit. Okay. The second one, well, we can analyze it in the same way. So this is going to be 1, 2, 3. And then this is going to be equal to square root of that plus 1 minus square root of that number. Okay. It looks like it's also getting smaller. It's certainly, well, no, the first number is bigger than the second one, so it's certainly greater than 0. But you can see that the picture is the same. It gets closer and closer and closer to 0. Okay, let's see if we can prove that. Oh, sorry. Here, we need to understand that n squared is a more powerful function than n. Even though it is 10,000 n, 10,000 n is linear, and n squared is quadratic. Quadratic grows quicker than linear. Right? If you have a linear function and a quadratic graph will always go above a linear graph. No matter what type of linear graph it is, it will intersect and go above. So it's the highest power wins, basically. The highest power beats higher power beats lower power. The value, yeah, you could look at that. But this is a different type of beast. So what we can do is we can manipulate it and say, okay, we have this. So square root of n plus 1 minus square root of n. We can rewrite it as square root of n plus 1 minus square root of n multiplied by square root of n plus 1 plus square root of n. If you ever done rationalizing the denominator, you know what I'm doing. Square root of n plus 1 plus square root of n. So what I did is I multiplied the top and bottom of this fraction by square root of n plus 1 plus 1 plus n, the square root of n. Now, if I expand the brackets, here, I get n plus 1 minus n divided by square root of n plus 1 plus square root of n. And that is square root of n, this 1 over square root of n plus 1 plus square root of n. And we can see that this thing, the bottom part, tends to infinity. And 1 divided by infinity tends to 0. So the limit of square root of n plus 1 minus square root of n as n tends to infinity is 0. Okay, can anyone guess what this one is? Limit of 1 minus 1 over n tends to infinity. It does tend to 1, of course, because it's 1 minus something really, really small. That does tend to 1. And remember, I taught that limit is linear. So you could do limit of 1 as n tends to infinity minus limit of 1 over n as n tends to infinity, because limit is linear. And that means you could, this is 1 minus 0, which is 1. Now this is a very special one. Does anyone know what this one is? Haha, Zeno. Yes, it is. So what is this? Like what do we see here? So it's going to be 1 plus 1 over n. So that tends to 1. That tends to 1. And 1 in any power is 1, right? But on the other hand, this tends to infinity. So we have sort of 1 to the power of infinity, which is not necessarily 1. Probably. And 1 to the power of infinity is probably not infinity. So it's somewhere between 1 and infinity, basically. Let's see. Let's see if we can make sense of that. I'm going to use Excel again. So here's going to be 1, 2, 3. And here I'm going to type in 1 plus 1 over that to the power that. And the first value is 2, unsurprisingly. Yeah, let's check. That is going to be 1 plus 1 over 1 to the power 1 is 2. 1 plus 1 over 2 to the power 2 is going to be 1.5 to the power 2, which is 2.25. Let's see. Yeah, it is. 1 plus 1/3 to the power 3 is going to be 4. It's going to be 64 over 27, which is 64 over 27. That's going to be 2.37. 2.37. Aha. Okay, so let's check. Yeah, it looks like there is a limit. It's getting, the numbers are getting, still growing. Two 176. 2177. Okay, I think we need to it's going to be 1, 10, 100, 10, 100. Will it do that? 136. 10, 1000 equals 10 times 10. Okay. Okay. We've just broken down Excel because the number is incorrect. And as you can see, Excel have just broken down because cannot really calculate powers when they are so big, because it implies the Excel had to take something to the power of 10 to the power 19, which is ridiculous. Okay, but we do see some if we do that, it is correct up to here. Up to here, it is correct. Everything else is broken down. We broke Excel. So in fact, yeah, it is the number called the number E, sometimes called the Euler's number, not Euler's constant. That's sometimes confusing. Yeah, but overall, the limit by definition, the limit 1 plus 1 over n to the power n is E as n tends to infinity. And that is by definition. So E is defined like that. So E is 2.718281828459045. I don't know the rest. Okay, so it's an infinitely long decimal, similar to pi, and just as important as pi. Okay, any questions? Okay. All right. Now here we just need to show that. Show that. Do I want to talk about the definition of the limit here? Let's see if we can make sense of it. This is not even studied at A level, not even in further maths. This is university material. But I don't think it's very difficult to grasp. A sequence has a limit if for any positive number epsilon, there exists an integer n that for any n small n larger than n, we have an minus l is less than epsilon. Let's try to apply this rule for this sequence. So n over 2n, 2 to the power n, has limit 0 if for any positive epsilon there exists n such that for any n larger than n, we have an minus 0 is less than epsilon. But an is that, yeah? An. So it's going to be n over 2 to the power n has to be less than epsilon. So you can rephrase that. Epsilon being the error. It's the difference between the limit and the actual value of the sequence. Because here is the sequence minus the limit has to be less than epsilon, where epsilon is an arbitrary small number. But yes, I think I know what you mean. So effectively, yeah. We can rewrite the whole statement is limit of n tends to infinity of n over 2n equals 0 means that for any epsilon greater than 0, there exists n such that for any n greater than n, n over 2 to the power n is less than epsilon. Don't worry about these. These are these are quanters. Anyways, so let's say epsilon is 0.1. Epsilon 0.1. You can find n such that for any n greater than n, the sequence n over 2 to the power n is going to be less than 0.1. So basically, whatever value you choose, you can see that the difference between this and the limit is going to be less than 0.1. So let me just draw this so that hopefully it makes more sense. So this is 1, 2. And this is going to be equal to this divided by 2 to the power this. 0.5. So this is n, and this is an, right? This is n, and this is the number of sequence. If for epsilon equals 0.1, there exists n equals 5, such that for any n greater than 5, so starting from for any n greater than 5, so 6 and above, the value of an is going to be less than 0.1. And it is. So starting from number 6, they're all less than 0.1. Now for epsilon 0.01, for example, there exists a number n equals 9. That means for any n greater than 9, an is going to be less than 0.01. Now for epsilon equals 0.001, what is n? There exists. I'd like everyone to answer, please. And if you don't know, please write I don't know. So from any point, the value an must always be lower than that point for the limit to exist. Yes. And epsilon can be anything you want. Yeah, whatever you choose, no matter how small epsilon is, you will always find a number starting from which the sequence will be lower than that value. All right. So for epsilon is 0.1, there is n is equals 13 indeed, such that for any n greater than 13, an is going to be less than the modulus of an. Sorry, the modulus of an. This particular case is less than, because it could be a flip-flopper. It could be positive and negative. Is 0.001. All right. So that means if there you have a sequence and this is the limit, and let's say A1, A2, A3, A4, and here is an epsilon. So this is the limit plus epsilon and the limit minus epsilon. No matter how small epsilon is, starting from some value of n, all the values would fall in between into that. Okay. All right. So we work out n from epsilon. How do you work out n from epsilon? So you choose an epsilon. Okay. Epsilon is your choice. I choose epsilon to be 0.03, for example. And then I can see that the values up to 8 are bigger than 0.3, and the values starting from 9 are smaller than 0.3. That means capital N is 8. That for any n which is greater than 8, the an is going to be less than 0.03. Yes. Whatever you choose, that determines the value of n. But the definition says that whatever your choice of epsilon is, you will always find an n suitable for you. If you can't find that n, that means it doesn't have a limit. Okay. So let me show you an example of a sequence that doesn't have a limit. So a very simple one, 1, 2, 3, and this is sine equals sine of that value. So you can see there's no limit. If you want to say, for example, epsilon is 0.1, you will not find an n such that starting from n, they will always be less than 0.1, for example. It just doesn't work, right? Okay, let's say 0.1, 0.1, 0.1, 0.1. Is there any less than 0.1? Okay, this one is less than 0.1, but the next one is bigger, so it doesn't work. All right. Okay, Mark, sir, sure. Okay, so that is the definition of the limit. Don't worry if you don't understand it. As I said, this is university stuff, not even further maths A level. Okay, but if you get a grasp of this, it's really, really good. So starting from whatever small value of epsilon you choose, if all the values starting from n fall into in the vicinity of the limit, that means that is a limit. Okay. So let's see. Okay. So let's say you choose an epsilon and you have a sequence n divided by 2 to the power of n. And that means for any epsilon, so it's n divided by 2 to the power n is less than epsilon. Can you actually do that? So n is less than multiplied by 2 to the power n. 2 to the power n divided by n is greater than epsilon. Is 1 over epsilon. No, sorry, I don't think you can easily find a function here. But anyways, what you need to focus on here, you don't need to focus on the definition of the limit. What you need to focus on here is that n is a linear function. That is n. And 2 to the power n is a power of 2. So n is 1, 2, 3, 4. And 2 to the power n is 2, 4, 8, 16. This grows quicker. Right? So this grows quicker, and therefore you can deduce that this divided by that will tend to 0, because you're dividing a number that is slowly increasing by a number which increases really quickly. I don't want to go I don't want to go too very deep into this, but I want you to get an intuitive feel for this. What about the second one? 2 to the power n divided by n factorial. Why do you think it is 0? Why do you think it would be 0? N grows faster because here you multiply by 2 every time. You times by 2 every step. But factorial, you times by n every step. That means it does grow much quicker. So start with 2, 4, 8, 16. Whereas here you have 1, 2, 6, 24, 32, 64, 624, 120, 720. So it grows much quicker. N factorial grows quicker because you're multiplying by n every time. And the same logic applies here. Here you multiply by a every time, times by a. And here you times by n and n is always increasing. It's bigger and bigger and bigger. Okay. A sandwich theorem, or the two policemen theorem. You need to show that the limit of this thing is 0. Okay. So what is the sandwich theorem? The sandwich theorem states that if sandwich theorem, if a n, if you have three sequences, a n, b n, and c n, if a n is less than b n and less than c n for any n, and the limit of a n is equal to the limit of c n, and n tends to infinity, and that's equal to, let's say, L. So if a n has a limit and c n has a limit, and they have the same limit, then the limit of bn is also L. What does that mean? That's the sandwich theorem. You have three sequences, an, bn, and cn. And you know that bn is smaller than a, is greater than an and cn. Now, if cn tends to L and an tends to L, that means bn also tends to L. Also, so if why two policemen? Because if this is you, this is policeman number 1, and this is policeman number 2. You're holding hands, and if this policeman is going to the police department, and this policeman is going to the police department, where are you going? That means you're also going to the police department. So if this sequence is going to L, and this sequence is going to L, and you know that you are stuck between the two sequences, that means you're also going to L. So yeah, this is called the sandwich theorem or the two policemen theorem. So how can we apply this here? The 2 plus sine n is a wibbly wobbly thing. We don't know what it is. It's always changing, it keeps changing. But we certainly know that 2 plus sine n is definitely greater or equal than 1. Because the smallest value sine can take is -1. Oh, let's put it like that. We know that sine n is greater or equal -1 and less than or equal to 1. That means that 2 plus sine n is going to be greater than 1 and less than 3. And that means that 2 plus sine n over n is going to be greater than 1 over n and less than 3 over n. But if this policeman tends to 0, because 3 divided by infinity is 0, and this tends to 0, 1 divided by infinity tends to 0, that means that this is also tends to 0. That means the limit of 2 plus sine n divided by n, as n tends to infinity, is 0. Okay. And the last thing I want to show you that sequences and series go way beyond what we are doing here, and what you're doing in school. And just a taster for you of them. Now, I don't know if you know, but your calculator doesn't know what sine is. You can't explain what sine is to a calculator. I don't know if you ever thought of that. Like, sine is opposite over hypotenuse. Yeah. But the calculator is wait, the calculator knows how to do sine 30 degrees, right? Sine 30 is 1/2. But how does it do that? Does it remember every single value for sine and cos? Does anyone know how it does that? It does. Yeah, it uses an approximate function. I'll just take a snapshot of that. Okay, that's not very useful. How does it know? How does it know? Does it know? Because sine is not something a calculator can do. It doesn't. I assume it also remembers certain values. I don't think it does that. I don't think it remembers certain values. I think it just uses an approximation. Well, it turns out that a sine can be written as a series of powers of n, because it is very easy for a calculator to multiply and divide, right? Adding, multiplying, and division is not a problem. So it turns out that sine x is approximately x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the power 7 over 7 factorial plus to infinity. A calculator cannot do that. Calculators, laters don't know how to do this, but they are very well, they know how to do this. They do know how to add and multiply. Okay. That's true for radians, right? It's not true for degrees. Because if you do it for degrees, it doesn't work. It's x is in radians in this particular case. But that's not the point. Let's see how this works. So y is sine x. This is a sine graph. Okay. And let's draw y equals x. Ooh, y equals x is actually very close to sine x for small values of x. And that's why we say for small values of x, approximately from minus 0.5 to 0.5 for small x, sine x is approximately x, because this is y equals x and this is y equals sine x. They're approximately the same because here they match. Let's carry on. X minus x cubed over 3 factorial. Ooh, would you look at that? It gets even better. Plus x to the power 5 over 5 factorial. It gets even better. Minus x to the power 7 over 7 factorial. And the more terms you write down, the closer it is to the real thing. And so you can see this is a really good match for quite a wide range of values. So pretty much from minus pi to pi, we've got a match. We've got a really close match, and this is using just up to 7. So this is y equals sine x, and this is y equals x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial. And all we need to do is just copy that function across, and that's how we can find, the calculator can find any value of sine x. Because the calculator does not know how to do this, but it does know how to do this. And it can do more if you wish. This calculator has a built-in accuracy. So you saw we've just broken down Excel because we've reached the limit of accuracy for Excel. So as you can see, it's approximately 12 digits, 12 significant figures, and then it just breaks down. Yeah, it is the Taylor series. It is the Taylor series. So yeah, power series. So cos x can be found as 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial plus etc. That's also to infinity. The more terms you take, the closer it is to the actual value. Yeah, so Yeah, it's why is it like that? It's yeah, definitely outside the scope. This is you need differentiation, which we haven't even touched. Derivatives. Okay, but also, if you ever heard that sine is an odd function, have you heard that sine x is an odd function? Sine x is an odd function, and cosine x is an even function. Even function. And look, sine x only contains odd powers of x, and cos only contains even powers of x. An odd function means it has a point symmetry. It has a rotational symmetry. Symmetry about origin. And the even function has a line symmetry. Symmetry in the y-axis. So, for example, y equals x to the power 4 minus 17x squared plus 15. Okay, that was too harsh. So that's an even function. Okay, because it's symmetrical about the symmetrical in the y-axis. And y equals x cubed minus 4x. And this is an odd function because it has a rotational symmetry around the origin. Okay. All right, we'll finish here. I hope that was insightful, useful, whatever. And yeah, so I'll see you next week then. That's great. See you.